This is S. Lakshmanachari, working as Assistant Professor in Department of Cybersecurity, Institute of Aeronautical Engineering, Hyderabad. In this lecture, we are going to discuss inter-process interconnection structures and inter-process arbitration. So, in this lecture, we are going to discuss the topics types of interconnection structures, followed by introduction to bus arbitration, and then we are discussing the different types of the arbitration algorithms. So we have two types of arbitration algorithms. One is a static arbitration algorithm and second one is a dynamic arbitration algorithm. So let's start with the interconnection structures. So a multiprocessor system, it consists of a set of modules like CPU, memory and IO processors. So all that communicate with each other. So that is a multiprocessor system. So here all these modules, so all these modules, they are communicating with each other. Okay. So the collection of paths connecting the various modules is called interconnection structures. So in a multiprocessor system, we have multiple modules. So all that modules, they needs to be communicated with each other. So in order to communicate with each other, in between them, we have a physical configuration. So that physical configuration is called interconnection structures. Okay. So the collection of paths connecting the various modules is called interconnection structure. So this interconnection structure is a physical configuration, and the design of this structure will depend on the exchange that must be made between the modules. So the interconnection between the components or modules can have different physical configurations. So that depends on the number of transfer paths that are available between processors and the memory in a shared memory system. So here you can see a multiprocessing architecture. So in a multiprocessing architecture, we have a multiple processors, CPU 1, CPU 2, 3 and so on, and memory. Okay. So in order to communicate one processor with another processor, in between we have a physical configuration. That physical configurations are called interconnection structures. So there are the several physical forms are available for establishing an interconnection network. So some of them are the time shared common bus, multi-port memory, crossbar switch, multi-stage switching network, and hypercube system. So these are the different schemes that are used for establishing an interconnection network. So first one is a time shared common bus. So as the name describes, time shared. So that means a common bus is shared by a multiple processors on a time basis. So that is called time-based common bus. So a common bus multiprocessor system, it consists of a number of processors connected through the common path to the memory unit. So here you can see the diagram. So we have a multiple processors, CPU 1, 2, 3 and IO processor 1, IO processor 2. So all these processors are connected with each other and they are connected to the memory unit through the common bus system. So this is a common bus system. This is a common bus. So through this common bus, all the processors, they are communicating with each other, and also all that process, they are communicating with the memory unit. So here the main difference between The CPU and the IO processor is the CPU. It can execute the arithmetic and logical unit operation. So the CPU, it will execute different arithmetic and logical operations. So that means arithmetic operations are addition, multiplication, division, and so on. And the logical operations are AND, OR, XOR, complement, complement, clear, increment, decrement. And coming to the shift operations, that are logical shift, arithmetic shift, and rotate shift. So all these operations are performed by the CPU. And coming to the IO processor. So the IO processor, it can execute the instructions which are related to the input or output devices. So that means we are performing two types of operations with the IO devices, that are IO read and IO write. So these two types of operations are performed by the IO processors. So in this time shared common bus organization, uh, at a time only one processor or one controller can communicate with the another processor or controller on a time basis. So that means suppose if the CPU 1 wants to communicate with the CPU 3. So this CPU 1, it is wants to communicate with the CPU 3, so that the CPU 1 is utilizing the common bus. So then it will be communicating with the CPU 3 using a memory system. So first the CPU 1, it is placed a valid data into the memory unit by using the common bus. After that, the CPU 3, it can access the same data which is available in the memory unit through this common bus. Okay. So only one processor can communicate with the memory or another processor at any given point of time. So only at any time, only one processor can utilizing the common bus. And the remaining time, all the processors will be in ideal state. That means they will not do any operation. So the transfer operations are conducted by the processor that is in control of the bus at the time. A command is used to inform the destination unit what operation is to be performed, and the receiving unit recognizes its address in the bus and responds to the control signals from the sender, after which the transfer is initiated. So the transfer conflicts must be resolved by incorporating a bus controller, so that establishes priorities among the requesting units. So suppose if the CPU 1, CPU 1 and IO processor 1, if they both wants to access the memory unit at the same time, so then the memory transfer conflict will occur, because the condition will be only one processor can utilize the common bus at any point of time. But here the CPU 1 and the IO processor 1, both they wants to use the common bus in order to access the memory unit at the same time. So then the conflict will occur. So to overcome that conflicts, we are using a priority concept. That means we are assigning a priority to the all the CPUs. So based on the priority, the buses will be allocated. Suppose if you see, suppose if the CPU 1 is having 0 priority and CPU 2 is 1, okay, let's see the highest priority. Suppose if the CPU 1 is having highest priority, and the IOP2 processor, it is having the lowest priority. Okay, so if the CPU 1 and IOP processor 1, if they requested for the grant of the common bus, so the bus will be granted to the CPU1 first. After that, the bus will be granted to the IO processor 1, because the CPU1 is having the highest priority. So that's why the common bus first it will be allocated to the CPU1, and after that, after utilizing and releasing of the common bus, then that common bus will be allocated to the IO processor 1. Okay. So in this way, by assigning the priority, then we can avoid the transfer conflicts. A single common bus system is restricted to one transfer at a time. So at a time only one transfers will be takes place, because we are having only one common bus system. So the process in the system can be kept busy more often through the implementation of two or more independent buses to permit multiple simultaneous bus transfers. So suppose if you provide a multiple buses, then we can provide a two-way communication. That means simultaneous transfers can be takes place by providing the individual buses. Coming to the second one, multi-port memory. So a multi-port memory system employs separate buses between each memory module and CPU. So here in this diagram, we can see three processors and three memory modules are there. So all these processors and memory modules are interconnected through the buses. So because here individual buses are there, but previously we have used a common bus, but here a separate buses are used in order to connect every processor with the corresponding memory modules. Okay, so here the memory module is having, it is a three-port. It is a three-port memory module. That means the memory module it is having three ports in order to connect the three buses. So basically we have a three buses that are address bus, data bus, control bus. So the processor also having these three buses, but here we are using a common bus. That means the processor also having address bus, data bus, control bus. So the address bus of the processor is connecting to the address bus of the memory. Similarly, the data bus of the processor is connected to the data bus of the memory module. Similarly, the control bus of the processor is connected to the control bus of the memory module. So in this way, all the processors are connected to the respective memory modules, so that the exchange of the data will be easy. Transferring of data is easy. So memory module is said to have three ports. So already we have seen. So the memory access conflicts are resolved by assigning fixed priorities to the each memory port. The priority for memory access associated with each processor may be established by the physical port position that its bus occupies in each module. So the main advantage of the using this multi-port memory is we can achieve the high transfer rate. We can achieve high transfer rate because we are using we are using a separate buses. That means we can do the simultaneous transfers. So that's why in this method we can achieve a high transfer rate by using the multi-port memory. That can be achieved because of multiple paths between the process and the memory. And if you come to the disadvantage of the disadvantage, then it is a expensive memory. It has expensive memory control logic because the every memory it is having some control logic. So that's why it is having expensive memory control logic and a large number of cables and connectors. It requires large number of connectors and cables because if you compare the multi-port memory with the common bus system, here more number of connecting paths are required. And coming to the crossbar switch. So the crossbar switch system consists of several interconnection cross points between the processor buses and the memory module paths. So see here. So this is a processor. These are all the processors and these are the memory modules. So in between them we have a cross pointer. We have a cross pointer. So this cross point, it acts as a switch. It acts as a switch. So the buses of the processor and the buses of the memory module are interconnected at some point. So this point is called cross point. So this cross point, it will be represented by a dash, a square box. So this square box, it is acts as a switch, and that switch will determine the path between the processor and the corresponding memory module. So crossbar switch organization consists of a number of cross points that are placed at intersections between the processor buses and the memory module paths. A small square in each cross point is a switch that will determine the path from the processor to the respective memory module. And each switch point has control logic to set up the transfer path between the processor and the memory. It examines the address that is placed in the bus to determine whether its particular module is being addressed. So suppose if the processor wants to access this memory module. So first this processor, it will places its address in the address bus of the processor. Then that address will be connected to the memory. Okay. So this control logic of this switch will determine whether the correct addressed memory module is being accessed by the processor or not. So it also resolves the multiple requests for access to the same memory module on a predetermined priority basis. So it also resolves the multiple access requests. So that means suppose if this for this particular memory module, here we have different processor 1, 2, 3. So by using this switch point, we can avoid this multiple requests because only this switch will determine the which processor should be connected to the which module. Okay. So by using this switcher, we can overcome that multiple requests for the single memory from the multiple processors. Next one, multi-stage switching network. So the basic component of the multi-stage switching network is a 2 input 2 output interchange switch. So this is a building block because we are implementing the multi-stage network using a single building block, that is a 2 input 2 output interchange switch. So by using that switch, we can implement any multi-stage switching network. Okay, so here you can see some 2x2 interchange switches. Okay, so see here. So every switch acts as a 2-port device. 2-port. So it is 1 port. So this is 1 port. Port 1. This is a port 2. So that means 2 input terminals and 2 output terminals are there. So that's why it is called 2x2 interchange switch. Okay. So let's see here we have a 2 inputs. So input A, input B, and we have 2 outputs. Output 0 and output 1. So the input A, it can be connected to either of the outputs. That means the input A, it can connect to the either 0 or it can connect to either 1. Okay. So see, so this is a connection of how the input A, it is connected to the output 0. So that means it is a direct connection. And see how the input A, it will be connected to the output 1. So it is a connecting. It is connecting to the output 1. And coming to the B input. So B input, it is connecting to the input output 0. And coming to the last figure, that is connecting the B input to the output 1. Okay. So these are the various connections, how the multiple inputs are connecting to the multiple outputs. Then using this 2 by 2 switching switch, then we can implement a multi-stage switching network. So this you can understand with we have a two sources, we have a two processes P1, P2. Then how these two processes are connected to the multiple destinations. So this you can understand we are connecting some source here. We are connecting some sources. Here are the destinations. So using this multi-stage switching network, then how we can control the different destinations using the source. So see here. So we have two processes, P1, P2. Okay. So P1, P2. So here we have different. See, consider a binary tree shown in figure. Two processors P1, P2 are connected through the switches to the 8 memory modules marked in binary from 000 through 111. Okay. So here we have a two processors and we have 8 memory modules. So this multi-stage switching network, it shows how the two processors are connected to the 8 memory modules. Suppose, let's see, suppose if the P1 processor, it wants to access the memory module whose address is 101. So see here. So first P1, it will be connected to the output of the one output of the first switch. So it will be connected to the output 1 of the first switch. After that, it will be connected to the output 0 of the second switch. This one, output 0. And after that, it will be connected to the output 1 of the third switch. So finally, we will get 101. So that means the P1 processor, it is connected to the 101 memory module, so that that particular memory can be accessed by that P1 processor. So like that, any source can be connected to any destination. That means any memory module. Okay. So this is a multi-stage switching network. Coming to the fifth interconnection structure, that is a hypercube interconnection. So the hypercube or binary n-cube multiprocessor structure is a loosely coupled system composed of capital N is equal to 2 power n, small n. So processors interconnected in an n-dimensional binary cube. So each processor, it forms as the node of the cube. So each processor has direct communication with direct communication path to n other neighbor processors. These paths corresponding to the edges of the cube. So here you can see different cubes. This is a 1 cube, this is a 2 cube, this is a 3 cube. So in order to establish a 1 cube, so that means 1 cube network. So see here, we require two processors. So 1 cube structure has n is equal to 1 and 2 power n is equal to 2. So here n is equal to 2 power n. Okay. So see here, if n is equal to 1, okay, so if small n is equal to 1, then 2 power 1, so that is equal to 2. So that means we require two processors. In order to form this. Okay. And coming to the 2 cube. 2 cube means 2 power 2. So that means 4. So that means here we require 4 processors. We require 4 processors. So this is one processor, 2, 3, 4. So that 4 processors will act as a node of the cube. And coming to the 3 cube structure, n is equal to 3, 2 power 3, that is equal to 8. So it has 8 nodes interconnected as a cube. So here you can see how all that 8 nodes are connected. So it will form a 3 cube. Okay. So an n cube structure has 2 power n nodes with a processor residing in each node. Each node is assigned a binary address in such a way that the address of 2 neighbors differ in exactly one position. So if you look into the node 000, so the neighbor nodes will be differ only by a single bit. Suppose if you compare this and this, only the middle bit is changed from 0 to 1. And if you compare this with this one, if you compare 000 with 100, so only the first bit is changed from 0 to 1. So like that, if you compare the neighbor nodes, only the 1 bit difference is there. Okay. If you compare compare other nodes, then the 2 positions will change. Suppose if the node 000 wants to connect to the 011, so first it should be connected to the 010, then it will be connected to the 011. So routing messages through an n cube structure may take from 1 to n links from source node to the destination node. For example, in a 3 cube structure, node 000 can communicate with directly with the 001. But if the 000 node wants to communicate with other nodes, then it must cross at least 2 links to communicate with 011. So this is a 011. Suppose if the 000 node wants to communicate with 011, then it must cross at least 1 cross point. And coming to the inter-processor arbitration. So before going to the inter-processor arbitration, let's see what is arbitration. So bus arbitration, it refers to the process in which the current bus master access and then releases the control of the bus and passes it to the another bus requesting processor unit. So that is called bus arbitration. So bus arbitration is the process in which the current bus master access and releases the control of the bus, and then it will be passed to the other requesting processor unit. So that means here in a multiprocessor system, so multiple CPUs are there, and all that multiple CPU processors, they are communicating with the others using the bus. But at any point of time, only one processor can utilize the common bus. So that's why if one processor is utilizing the bus, and after transferring the data, then it will release the bus so that the another processor can can utilize the bus. So in this way, the common bus will be shared by all the different multiple processors. So this is called bus arbitration. So the processor that has access to the bus at an instance is called bus master. So whatever the processor currently accessing the bus, so that is called current that is called bus master. So a conflict may arise if the number of DMA controllers or processors try to access the common bus at the same time, but access can be given to only one of those. So already we have seen. So If multiple processors or they wants to access the same bus, then some conflict will occur. So this conflict will overcome by assigning a priorities to the processor. Always the highest priority processor can utilize the bus. Okay, after that lowest priority. So like that, the bus will be accessed by the multiple processors. Only one processor or controller can be bus master at the same point of time. So see, to resolve these conflicts, a bus arbitration procedure is implemented to coordinate the activities of all devices requesting memory transfers. So the selection of bus master must take into account the needs of various devices by establishing a priority system for gaining access to the bus. So bus arbitrator decides who would become the current bus master. So we have different arbitration algorithms that are mainly we have a static arbitration algorithm and the second one is the dynamic arbitration algorithm. So the static arbitration algorithm, it is further divided into two types. One is the serial arbitration, parallel arbitration. And coming to the dynamic arbitration algorithm, again we have four types that are time slice, polling, LRU, FIFO. So let's see one by one. First one is the serial arbitration algorithm. So what is serial arbitration algorithm? Okay. So first one is a static arbitration algorithm. So this serial arbitration algorithm is a come under the category of static arbitration algorithm. So static arbitration algorithm means in this type of algorithm, the priority of the device is fixed. So we cannot change the priority of the device. So suppose if you have a three devices or three CPUs, CPU 1, 2, 3. Suppose if you assign a highest priority to the CPU 1 and the lowest priority to the CPU 3. So once we have assigned the priorities to the devices, then we cannot change it. So that is called static arbitration algorithm. So arbitration algorithm service all processor requests on the basis of established priorities. A hardware bus priority resolving technique can be established by means of a serial or parallel connections of the units requesting control of the bus. So these priorities can be achieved by connecting the devices in a serial fashion or the parallel connections, serial connection or the parallel connections. So the serial priority resolving technique is obtained from a daisy chain connection of bus arbitration circuits similar to priority interrupt logic. So daisy chain connection, that means here all the devices are connected in a serial connection. So that means one after another. So the output of one device will be connected to the another device. So in this way, all the bus arbitrators are connected in a serial connection manner. So here you can see the serial arbitration. So these are the bus arbitrators. So every processor, it is having corresponding bus arbitrator. So suppose if you have a 4 processors, then we have to use a 4 bus arbitrators. So the first this is the bus arbitrator which is associated with the first CPU, and this is a bus arbitrator 2. It is associated with the CPU 2. So like that, every CPU, it is having its corresponding bus arbitrator. So this bus arbitrator will decide which CPU can take the control of the bus at any point of time. Okay. So see, so all these bus arbitrators are connected to a common memory. So that is called shared memory. Okay. So see here. So this is a bus arbitrator 1. So initially we are giving a logic 1. We are giving a priority input to the bus arbitrator 1. Then the bus arbitrator, it is having two, one input and one output. Okay. So it is having one input and two outputs. One is a PO, priority output. Then it is a bus busy line. Okay. It is a bus, common bus. It is a bus. Okay. So it is having one input, one output. That is a PI. Okay. Priority input. This is a priority output. Okay. So the bus arbitrator with PI is equal to 1 and P naught is equal to 0 will be given the control of the bus. Okay. So PI is equal to 1 and P naught is equal to 0 is the one that is given control of the system bus. Okay. So initially PI is equal to 1. Okay. After that P naught. Suppose if the P naught is 0. P naught is 0. So that means the bus arbitrator will be connected to the memory. Suppose if the P naught is equal to 1. If the P naught is equal to 1, then the P naught 1 will be given to the second bus arbitrator. Then the PA is equal to 1. Suppose if the bus arbitrator 2, P naught is equal to 0, then the bus will be given to the second CPU, second bus arbitrator. So like that, based on the priority only, that buses will be allocated. Suppose, see here. So this is a highest priority and this is a lowest priority. So always the bus will be allocated to the highest priority device. Okay. So when an arbitrator receives the control of the bus, that is PA is equal to 1 and P naught is equal to 0, it examines the busy line. So if the busy line is inactive, so it means that no other processor is using the bus. So if the busy line is inactive, so this is a busy line. So if it is inactive, that means no processor is utilizing the bus. Suppose if the busy line is active, that means that another processor is currently using the bus. Okay. So in this way, we can determine whether the bus is active or not. And coming to the another arbitration logic, that is a parallel arbitration algorithm. So the parallel bus arbitration algorithm technique, it uses an external priority encoder and the decoder. So we are using here two combinational logic circuits, that are priority encoder and decoder. So it is a 4x2 priority encoder, and here we are using a 2x4 decoder. Each bus arbitrator in the parallel scheme has a bus request output line and a bus acknowledgement input line. Each arbitrator enables the request line when its processor is requesting access to the bus system. The processor takes control of the bus if the acknowledgement input line is enabled. So see here. So these are the parallel arbitration algorithm. So here we have four bus arbitrator 1, 2, 3, 4. Okay. So whatever the bus arbitrator, it receives the acknowledgement that will be given the control of the bus. Okay. So see here. Okay. So suppose you see here. It is so here every bus arbitrator, it is having some one input and one output. So output is a request, bus request, and input is the acknowledgement. Okay, so see here. So the outputs of all the bus arbitrators. So the requesting output of all the bus arbitrators are connected to the input of the priority encoder, because it is the size of the priority encoder is a 4 by 2. So that means 4 inputs are there and 2 outputs are there. So this is I1, this is I2, this is I3, and this is a I4. So 4 inputs and 2 outputs are there. 2 outputs. Okay. So this is a priority encoder. So that means based on the priority, it gives the corresponding output. Okay. So you can see the truth table here. Okay. So see here. So these are the inputs. These are the inputs of the priority. Let assume this, you can assume D1, D2, D3, D4. So always the bus arbitrator 1 is having the highest priority and bus arbitrator 4 is having the lowest priority. Okay. So see, the bus request output lines for all the bus arbitrator is 0. That means no bus arbitrator is requested for the bus. So that's why outputs of all the bus arbitrators are zeros. Under that, the output is don't care. Suppose if the first arbitrator requested for the bus, so the output of the first bus will be logic 1 and the remaining all are zeros. So in that case, the output of the priority encoder is 0, 0. Suppose if the second bus arbitrator requested for the bus, then the D2 will be active high and the remaining all are zeros here. Okay. Next, then in that case the output will be 0, 1. And suppose if the third bus arbitrator requested for the bus, that third bit will be output of the third bus arbitrator will be active high and the remaining are active low. For that output will be 1, 0. Suppose if the fourth arbitrator output is logic 1, then the output of the priority encoder will be 1, 1. Okay. So these are the output truth table of the priority encoder. Okay. Suppose if the bus arbitrator 2 it requested for the bus, so it is requested, that means 1. The output of the request output of the bus arbitrator 2 is logic 1 and the remaining all are zeros. So what will be the output of the priority encoder 1? So 0, 1. Okay. When second bus arbitrator is active, output will be 0, 1. So 0, 1. So 0, 1 is there. 0, 1. So what will be the decoder output? 0, 1 means 2. So here this will be output and the remaining all are zeros. Decoder output. So it will be the output, this will be active high. So this is connected to the acknowledgement of the second bus arbitrator. So the acknowledgement for the second bus arbitrator will be, it will be 1 and it will be 0, it will be 0, it will be 0. So that means whatever the bus arbitrator it receives the acknowledgement, it receives a acknowledgement as logic high, that bus arbitrator will be taken the control of the bus. So now this will take the control of the bus here, then it transfers the data to a memory device. So it will transfer to a common memory device. So like that we can transfer by using this technique. So at a time only one processor can utilize the common bus. Okay. And coming to the second type of the arbitration algorithm, that is a dynamic arbitration algorithm. So dynamic means here in this type of algorithm, the priority of the device is not static, that means not fixed. So we can change the priority of the device. So discussed two bus arbitration procedures use a static priority algorithm. So the priority of each device is fixed by the way it is connected to the bus. So in contrast to the dynamic priority algorithm, so the system capability for changing the priority of the device while the system is in operation. So while the system is in operation, then we can change the priority of the device. Suppose we have a, see here, it is one device. Let assume initially it is having highest priority, it is having the lowest priority. But while the system is in operation, we can change the priority. That means this highest priority device, we can make it to the lowest priority, and similarly, the lowest priority device, we can make it to highest priority. So in this way, we can change the priority of the device while the device is in operation. So that is called the dynamic arbitration algorithm. So this dynamic arbitration algorithm, it can be achieved by using multiple algorithms: time slice, polling, LRU, FIFO. So time slice. So time slice means so every processor inside the multiprocessor system will be allocated for a fixed time slice. That means suppose the CPU 1 is there. So for that CPU, it has allocated some 3 milliseconds of time. So for that duration, the first CPU will be takes the control of the bus. After that, the CPU 1 will be disabled, and then the chance will be given to the CPU 2. So that again the CPU 2, it will be take the control of the bus for again another 3 milliseconds. So like that, the bus will be allocated to all the CPUs which are available in the system. Okay, so that is called time slice. And second one, polling. Polling. So polling is suppose if the first device wants to access the bus, then the CPU 1 will be sending a request to the bus. Then the bus will be allocated. After that, second CPU. Again, if the second CPU wants to access the bus, then the CPU 2 wants to send a signal to the bus arbitrator. So in this way, the buses will be allocated to the respective CPUs. That is called polling. So in the polling, it takes more time because if the last CPU wants to access the bus, it takes more time. And LRU, least recently used. Suppose if suppose if the CPU, let us assume this is a CPU 4. Suppose if the CPU 4 is not using the bus for a long time, but the CPU 1, 2, 3 are utilizing the bus frequently, but the CPU 4 is not utilizing for a long time. So that in the LRU algorithm, the first the bus will be allocated to the least recently used device. So that is a LRU. And the last one is a FIFO, first in, first out. So in, first out, whatever the first device will request for the bus, that will be allocated to the bus. Okay. And whatever the bus allocated to the CPU first, that will be released first. So like that, all the buses will be allocated to the CPUs in the form of FIFO, first in, first out fashion. Okay. So in this lecture, we have seen the different interconnection structures, and also we have seen what is the definition of the bus arbitration and the different algorithms we are using in the bus arbitration. So we have two types of bus arbitration algorithms. One is the static bus arbitration algorithm, and the second one is a dynamic arbitration algorithm. So we have seen all these different types. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.